Good evening, all of you. My name is Anil Yadav. I am from IISc Bangalore and I am here for the course of Fundamentals of Micro and Nano Fabrication. This is tutorial 9 and I am following the lectures of Professor Sushovan Avasti for today's tutorial. So you can have a look on Professor Sushovan Avasti's lectures as well, which are also available on YouTube and NPTEL. And okay, let's start. Today, in the previous session, we have discussed about the lithography. About after lithography, there is a subsequent process is etching. This is the next subtractive process, which is etching. Etching is nothing but it is just a removal of the material. Okay. Whatever you have patterned in the through lithography, but after that you can do the selective etching. So your photoresist will protect the layer, the layer underneath that, and whichever part is exposed to the outer environment, that part will get etched. Okay, so that so for the nano patterning, micro patterning, you can use this process of lithography and then etching, selective etching in the sense that won't etch the etch your photoresist or whatever is the protective layer for which for the wafer or underneath, so that will be protected, and the other part will get etched. Okay, so let us see the figure of merits of the etching. So figure of merits in the sense, what is the what do we need to care about while etching of the while removing the material on the from the substrate. Okay, mostly we are using the silicon substrate, so we will be looking for the silicon dioxide or silicon nitride kind of etching. Okay, so first is the etch rate. What is the removal rate of the material? Okay, in 1 minute how much thickness is getting reduced, that is the etch rate. Then etch uniformity, because as we are dealing with the wafers of different sizes, like 3-inch, 4-inch wafer, 5-inch wafer, so 6-inch, 7-inch, up to 12-inch of wafers are there in the market. Okay, and they are patterned like with the photolithography at once. Okay, like 12, if you are patterning on over a 12-inch wafer and then you are removing the material, okay, that uniform is there at certain part of the wafer. Let us say at this part of wafer there are smaller feature sizes, at this part of the wafer there are higher feature sizes. Let us say 100 micron is here, but at this point the feature size is just 2 micrometer. Okay, so their etch rate will be different for this, so we will see the etch rate uniformity as well. Or also there is a thickness difference of the material as well at this position, that the material will may be thicker and then this at this location, so that also there will be also uniformity, unknown uniformity because of that. Okay, NS isotope, we will deal with discuss with about the anisotropy and isotropy, we will deal with the, we will see what is anisotropy and isotropy. Okay, and selectivity in the sense, you have a wafer, this is the wafer, and you have deposited a material over there. Okay, so selectivity, you want to etch the material this material you want to etch. So how will you etch that particular material without etching this one? So what is the etch rate of this material, and there will still be the etch rate of this photoresist. Let us this is the photoresist and you want to etch the underneath material from this location. Okay, from the opening. So what is the etch rate of this material, this, let us say, silicon, then the photoresist. Okay, then the photoresist. Okay, that will be the selectivity. We will see in the subsequent slides. Okay. And now let us see one by one the figure of merits one by one. First one is the etch rate. Okay, so this is nothing but the measure of how fast the material is etched. Okay, initially when we put this substrate or whatever the material, okay, over that, this is the material, and we put this in submerged this in the container where the etchant is there. Okay, in that material, so we initial thickness minus final thickness after certain time t. Okay, initial delta d is decreased. Okay, this is this much of thickness is etched while submerged in the etchant. Okay, so the etch rate will be nothing but delta d by t. So the thickness removed in time t. Okay, that will be maybe nanometer or micrometer per minute. Okay, it is denoted in this. So the next figure of merit is the uniformity. Okay, uniformity is like in this one, what you can see is in this figure, what you can see is the opening. Okay, the opening is nothing but this is the feature size on the wafer that is transferred through the photolithography or any kind of lithography. Okay, so let us say this feature size is 50 micrometer. Okay, this is 20 micrometer, 25 micrometer. Okay, 25 micrometer, and this one is 5 micrometer. Okay, so there are so the etch rate for different openings will be different. Okay, because of the let us say the etch rate, you wanted to etch this much thick. Okay, this much of thick of this silicon. Okay, but here it is over etched, and here it is under etched. That is because of the opening. The recipe that was optimized is according to this 25 micrometer feature size. Okay, but at 50 micrometer it is over etched, and for 5 micrometer it is under etched, and that can happen, and this is required because over a wafer you have different sizes of the feature sizes. At this place you can have a die with the 5 micrometer feature size. At this point you can have a die with the 100 micrometer. Okay, so you are transferring the pattern in a single go with the lithography, and then you are etching. Okay, then you are etching that at that point. So this 5 micrometer feature size will have a slower etch rate, and this 100 micrometer feature size will have a higher etch rate. Okay, so because of that the non-uniformity comes. Okay, the etching. So another the this is very sensitive. Actually this is very sensitive because, and that is because there are two things happening here. Okay, once whatever there is a etchant is there, and the etchant is reacting with the silicon and it is forming some complex or something, there is a product. Okay, that product is here at this position. Okay, that and during that period this fresh etchant should go inside to react with the fresh silicon. Okay, let me check, someone is there. Okay. So during that period, but during this time, what happens is there is a reactant as well as there are products. The product is cannot be reused for the etching, further etching, but that is inhibiting to for the fresh agent to come. Okay, if the feature size is larger, there is very good path to go out. Okay, but if the feature size is lower, then what will happen is it will inhibit to for the fresh agent to come, and there will be a lesser etching. Okay, the etch rate will be lower in this case. Okay, and also uh, it it should be very for it is very sensitive to the temperature and agitation. Temperature okay, temperature increases the etch rate. Okay, the reaction rate with of at this position it increases. Okay, there are two things happening. One is the diffusion of this fresh agent to this place, okay, from in this direction, and another one is the out diffusion of the product. Okay, one is the diffusion happening, and another one is the this reaction at this interface of the fresh agent with the silicon. Okay, so if we increase the temperature, that reaction will increase. Okay, so that that is nothing but the kinetics. Okay, okay, that reaction will increase, and it reaction H rate will be faster. And agitation, in agitation, whatever the product is there, agitation in the sense we are just agitating we are just giving some vibrations to the if that is in the petri dish, there is agent in the petri dish, and we are putting our wafer in the petri dish in that agent, and we are slowly keep it vibrating or with our hand with the tweezer, so that whatever the product is there, that can go out, and the diffusion of the we can, so that we can increase the diffusion. That's it. Okay, so so that we can do while doing, but also the agitation is not also non-uniform. Okay, so at one position it is the diffusion is faster, at the another position the diffusion is slower because of the non-uniformity of the agitation as well. The another thing is, the in reality etches are non-uniform because of the dry etch is more than wet etch. Dry etch is more non-uniform because of the flow of the gases. Okay, deep etch is more than the shallow etches. Non because deep etch is there is should be a out diffusion as well, and in diffusion as well. If you are going for a 50 micrometer inside the you want to make a trench of the 50 micrometer, or if, and another thing, you are making a trench of the 10 micrometer. Okay, so that says that if a deep etch is which is more uniform, which is slower. Okay, that is slower, and shallow etch is which is can be faster because of the uh, you no need to go that much deeper. Okay, okay, fast etches have more than slow etches. Okay, fast etch is more non-uniformity is in the fast etches is more because you do not have that much control over the etching. Okay, in slow etches or in slow etches you can have a control over that. Let us say if you want you want a trench of let us say 10 micron, and there is a etch rate. There are two agents with the etch rate 5 micron per minute, micrometer per minute, and one is 10 micrometer per minute. Well, maybe 10 let us say 100 micrometer per minute. Okay, so this 100 micrometer per minute will take just 10 seconds. Okay, if you increase just 1 second, that will increase the depth of the trench. Okay, in 1 micrometer per minute, if you increase the time just by 1 or 2 seconds, that won't have a much effect on the trench on the trench. Okay, this is the thing, because the faster it achieves, we have a control on that thing. And now the variation in etching time could be due to variation. Okay, in etching time can be there is a film etching rate. Okay, film etching rate is completely depend on the etchant. Okay, and the etch rate, let us say, is RF. This is a variation factor that depends on the feature size. Okay, this is the variation which depends on the feature size. And another thing is the film thickness variation. As we have a 4-inch wafer, everywhere we cannot have a same film thickness. Let us say this is the wafer, and the film thickness like this. Okay, at edges the thickness of the film is higher and then in the middle of the wafer. Okay, so because of that, and that film thickness will maybe HF, maximum film thickness can be HF into 1 plus delta. Delta is the variation factor which varies with the distance. Okay, so in first this is the minimum and this is the maximum. Okay, so etching time, okay, at this position you want to etch where the thickness is maximum, because you want to etch this much of thickness. Okay, this much of thickness. So how this is the maximum height, maximum film thickness, HF max. Okay, this is the minimum this etch rate. Okay, the ratio of these will give you a worst etching time. Total, that will be a total time that is taken by this one. Okay, so this is the you need to take care of. The film should be uniform. Okay, if there is a much more variation in the film, then you will get you won't get a desired feature. Okay, desired thickness, desired trench height or something, whatever you want to do. Okay. And now comes on the third aspect, third figure of merit, which is isotropic. And first let us understand what is the isotropic and anisotropic. Isotropic etch is let us say this was the opening through the photoresist, and you want to etch this film. Okay, etch this film. So your etchant will come from this direction. So at this position it will start etching. Okay, so at when there will be at this much of the film is etched, at that point what will happen is this portion at these edges, let us say this. Okay, let me change the color. At this position, so this silicon is, let us say this is silicon. Okay, this is silicon. So this silicon is also exposed. Okay, so exposed to the etchant. So there will be etching in this direction also. So there will be a kind of a spherical kind of edges will be there. So uniformly it will etch out, and below this photoresist the desired feature size was this much, but we are getting this much of the feature size. Okay, so sometimes it is desired or sometimes it is not desired. While making the cantilever it is desired. Okay, this is desired so that we can under etch. Okay, so to form a cantilever kind of thing. So this is a isotropic etch. Usually wet etching technique, because of the this liquid. Okay, liquid etchant is in continuous contact with this silicon, so it will slowly etch inside walls as well. In anisotropic etch, what happens is there is like kind of the etching will be in single direction, okay, in unidirection. So it won't etch this side, but it will etch in this direction. And this etching is done by usually dry etching with the ions. Okay, the bombardment of the ions is directly go from top to bottom, so there is no deviation on the sides. So that is why there is a a dry etching process, and this uses gases. Dry etching uses gases. This is wet etch which liquids, okay, liquids. And this is generally we can get this anisotropic in the dry etching. And still this is not perfectly anisotropic, but there is a small undercut as well, okay, during that etching. And because of some deviation from of the gaseous molecules, and also there are some other factors as well that we will discuss in there. Okay, so another thing is in anisotropic, this is anisotropic. In anisotropic, reaction rate limited etching. This is a reaction rate limited rate limited, as we have studied in the diffusion. Maybe in CVD you have seen that there are two things. One is the diffusion of the gases from that laminar flow or through that stagnant layer, okay, through that stagnant layer till the surface, okay, till the surface. So that is the diffusion. And there is happening the there is happening the reaction, okay. So reaction is reaction rate limit. Reaction is slower than the diffusion, okay. Reaction is slower than the diffusion at this point. So there is a enough precursor is available, or enough etchant is available which can etch the sides as well, okay. That is why this is anisotropic. Okay, not anisotropic. This is actually isotropic etching happens, which is diffusion rate limited. Oh, sorry, I just confused. I got confused. So diffusion rate limited happens in the isotropic one, and reaction rate in anisotropic happens because of the reaction rate limited. And okay. So in these cases, so the mild agent with the low reaction rate is there because of reaction rate limited. We need to reaction rate limited. And dilute agent in the sense that the reaction rate there will be very lesser number of molecules of the agent which can be diluted in maybe in DI or some other solvents, okay. So, and this is concentrated and viscous and aggressive agent with a rapid reaction rate. Okay, let us see let me see the undercut, okay. Because of the isotropic etching, what happens is there is this is the photoresist, and this is your, let us say, SiO2, okay. You want to remove the SiO2 from this point only, okay, from this point only. That you wanted it to be perfectly anisotropic, but it is isotropic, yeah, because of that. And this DF, you got the feature size that you got after the etching, and whatever you wanted DM, okay. So this is the undercut. What is the undercut? This much, okay. DF minus DM, double of that, okay. DF minus DM, because this part plus this part is the extra that you didn't want, but it is there, okay. That is the thing that this was the desired feature size. In another case, this was the desired feature size, but you got you wanted a pillar, okay, pillar like structure of this one. So because of undercut, the pillar size, the diameter of the pillar was df. Okay, so in this case dm minus df will be the undercut. Okay, in complete anisotropic edge, complete isotropic edge. Okay, complete isotropic edge. So this in this case, uh, uh, complete vertical etching is equal to the lateral etching. Okay, this hf will be equal to c is equal to hf. Okay, we can say that will be there because of the isotropic etching. The complete whatever etching is there, that this part plus this part will be there. Okay, c will be that much. In anisotropic, because in anisotropic the unidirectional etching will be there, and this part won't get removed, but this part will get removed, and dm minus df will be 0. Okay, in this case, or df minus dm will be 0 in this case. So that is the c is equal to 0. Okay, so another thing is the degree of anisotropy. Degree of anisotropy, we can say we can measure the degree of anisotropy from the in this case there is an undercut, which is because of the isotropic etching. Okay, and this is also there because of the isotropic etching. So this was the feature size that you desired, dm, and but what you got is the df. Okay, so lateral etching. Okay, lateral etch rate, this side etch rate, what is the etch rate of the material, this silicon in lateral side, this is the r lateral, and this side etch rate will be the r vertical, which is the vertical height. So af, degree of anisotropy, is given by 1 minus r lateral by r vertical. Okay, if that is the isotropic etching, then it will be 0. Otherwise it will be in between, or for the anisotropic etching it will be 1. Okay, so that is the case. And for isotropic etching, because of the isotropic etching, lateral and vertical will be equal. Okay, lateral and vertical will be equal, and that is why this is 1, this is 1, this is equal, so that will be 1. 1 minus 1 is 0. That is isotropic. Now comes in the selectivity. Okay, just now comes with the selectivity. In selectivity, this is the etching mask. Okay, let us say this is the photoresist, whatever the photoresist is, this is positive or negative photoresist, that doesn't matter, but you have pattern with the photoresist over the, this is Si, this is SiO2. Okay, so you want to protect this layer below this one, you want to protect this layer, and you want to etch this part. Okay, this part you want to etch. Okay, this part you want to remove. So when you are etching, so when you keep this in a let us say in a wet, during through the wet etching, you put this in a petri dish with etchant. So as you submerge, so there will be etching of this photoresist as well. Okay, you have selected this some etchant, so that the etch rate of this material, silicon dioxide, is more than the etch rate of this RB. Okay, so that is the thing. So the selectivity is given by SAB is RA. RA is the etch rate of the material that we want to etch, and RB is the etch rate of the mask layer. Okay, so this is the ratio of these films. And this S is controlled by the chemicals, because which chemicals agent we are using, it depends on that. Okay, and the concentration, more is the concentration, more will be the H rate. Okay, and also that is also selective. And temperature, if we increase the temperature increases the reaction rate. That can be faster for some, and can be slower for other. So that also affects the selectivity of the etching. Okay, now let us come on the wet etching. These were the figure of merits that we have discussed. Now we will come on the wet etching. Wet etching is the process of removing the material through the by means of some solutions. Okay, so so this is nothing but that you have already seen. As we keep this in a bath with the filled of completely filled with etchant. So there are two things. One is this diffusion of this fresh etchant to the fill, and there is out diffusion. Okay, one is diffusion, in diffusion, one is out diffusion, and this process is the reaction. Okay, this process is the reaction. So first, this reactant transport to the surface, this is the diffusion. First process is the reactant transport to the surface. And selective and controlled chemical reaction. Selective and controlled chemical reaction is this should not react that much faster with the etching mask, but it should react with the layer which we want to etch away. And controlled chemical reaction is the etch rate we need to control. Okay, and also transport of byproducts away from the surface, this third process, which is the transport of the byproducts. And also these byproducts must be soluble in the solvent. Sometimes these are the complexes which are soluble inside in the solvent, and when we agitate it, they get out diffused. Okay, that is the thing. So we will see subsequently. Now let us see the kinetics. Okay, so there are two things. One is the surface reaction rate limited. Surface reaction rate limited is that this process, second process, is slower than the diffusion of the reactant of the reactant to the surface. Okay, diffusion is there. There is sufficient material or sufficient reactant material is available at this position, but reaction is not that much faster. Okay, so chemical reaction, bottleneck is chemical reaction between the film and the etchant. So okay, this reaction is not that much faster, which is the bottleneck. And another thing is diffusion rate limited. In diffusion rate limited, this reaction is faster, but this etchant, or we can say that reactant, is not that sufficient in that sufficient amount available here. Okay, so that is because of the diffusion is not happening properly, or we can say diffusion is slower in this case. So the diffusion is the bottleneck. That is why because of that stagnant layer. Okay, stagnant layer is because of the maybe because of the byproducts, or because of the less this is available, less reactant is available. Okay, so this H rate depends on this surface reaction rate limited. Okay, this H rate depends on the temperature. If we increase the temperature, reaction rate increases. Okay, sometimes it is 2 times per 10 degrees Celsius. If if it was, let us say, we are doing at 20 degrees Celsius at the inside clean room. So if we increase the temperature on the hot plate to 30 degrees, it will be twice. Okay, the reaction will be twice. So we can control this with the temperature, and this is the stirring and agitation. So that that steers the solution so that the products get out diffuses or in diffuses, the reactants can get in diffuses, so there will be a availability of the of the of the material of the reactant at the surface to etch. Okay, so what are the conditions for the reaction rate limited is the if you want to be in the regime of the reaction rate limited, then the temperature should be lower. The agent should be diluted enough so that the availability is also lesser at this position, and because of the stagnant layer, the diffusion of the material is lesser in this case. Agent should be weak, so there will be a reaction won't happen, reaction is not happening at all because of that. Okay, then diffusion rate limited. So is you can increase this okay this at high temperatures. Okay, you can diffusion is at this position at high temperatures. What will happen is, at high temperature reaction will be faster. Okay, but the diffusion is not that much faster, so that there will be availability of the reactant at that interface. Okay, but the reaction is faster because of the high temperature, so we will go in the regime of the diffusion rate limited. If there is the viscous and the concentrated agent, if the agent is more concentrated and more viscous, then there is a diffusion of that will be not that faster than the reaction rate. Okay, aggressive agents. In aggressive agents, what will the reaction is faster because of the aggression. Aggressive in the sense the reaction times chemical activity. Okay, if the reactant is aggressive, the agent is aggressive, then reaction is happening faster, but the diffusion is not there. Okay, so we will be in the regime of the diffusion rate limited. Okay, how will after this etching, so how the surface will be look like, how the surface finish will be there? It will be rough. Okay, because of the reaction rate limited, it will be rough and possibly anisotropic. Okay, and if you want to get a smooth and shiny surface, you should go in a diffusion rate limited process. Okay, so in contamination level, if we see that contamination level is lower in this case, but in this case it can be higher. Okay, for what application it is used, this kind of reaction rate limited or diffusion rate limited is used is for the cleaning purpose. For this is used for etching purpose. If you want to do for electronic applications. Okay, for the electronic applications, you need a smooth and shiny surface. Maybe for photonics or MEMS photonics applications, you may be using this one. Okay, now general mechanism, we will go on a, not only the chemical reaction is happening at the surface, but there is an electrochemical corrosion is also happening. Electrochemical reaction is also happening because of the domains. These are the micro domains or nano domains at on the surface, which are created because of the etchant. Okay, they are just random and they keep changing their position. Okay, they keep initially it is here, then it may go here. Okay, that can that may be changing. It is positive in some in now, but after some time it can be negative. So it keeps changing continuously. Okay, with time domains, both the cathode and anode. With the time, domains act as both cathode and anode. Okay, so now these are micro domains, as I told you, cathodes and anodes. So and now with for with like if there is a, if we give the enough time, so that will average out everything. Okay, this will lead to the uniform deposition. Okay, this will lead uniform etching actually. Okay, this will lead to a uniform etching, because everything will be averaged out after some time. If you give a sufficient time, it will be averaged out. And now doping and defects on the semiconductor affect etching. So like if we will see that highly doped semiconductors have a less etch rate, okay, for etch stops, or and will be useful for the etch stops and defect etches. So if there is a semiconductor, okay, which has a very highly doped in this region, and so if you want to etch this region, this one will get removed, but till here you can do the etching, so that will stop the etching after that. Okay, temperature, if you increase the temperature, obviously the it will be increasing, the etching will be increasing. Okay, so we one by one we will see now. Okay, so let me turn on. Okay, now let us come on the oxidative etching. Oxidative etching, most of the etching involves the oxidation. Okay, because it is the reverse of the deposition process. So what we have done is the deposition of, let us say, native oxide. Okay, so in that case there was a reducing of the silicon. Okay, so no deposition of not the oxide, deposition of silicon. Okay, deposition of silicon is from the through the CVD or something. Okay, so that will be so now that was the reducing. So now we need to do the reverse of that, that is the oxidation. First we will do the oxidation, then we will make the complex of that Si, and then we will remove it. So that we will see it dissolved in some, so oxides. So first we will form the oxides of, let us say this is silicon, we will convert it into SiO2, and this SiO2 will be dissolved in HF, and this which forms a complex, and this HF will be then it will form a soluble complex, and it will be removed. Okay, so these need to be dissolved in some acids. This silicon dioxide is dissolved in some kind of in HF or some phosphonic acid, we will see. Okay, okay, let me check on. Okay, so now first this metal will be converted into metal oxide, which will form which will react with some reactant that will form a complex with that reactant, and then this metal will be, this complex is dissolved in that solution, because this is dissolved, and this fresh oxide, a fresh semiconductor, then it will come in this position again. Okay, for insoluble oxides we need to form complex. These SiO2 are insoluble, so we need to form a complexes, so that we will see how we will form the complex. Okay, so wet etching characteristics, let us see what are the advantages and disadvantages of the wet etching first. So wet etch process are generally isotropic. isotropic in the sense they etches in all the directions, and because of that these the walls are smooth in this case. But there is a poor side wall control. We just not critical for non critical feature sizes. So because we just wanted a 2 micron feature size, but in the end we are getting a 3 micron feature size, so that is not desired. So etch rate varies with the temperature. Okay, if we increase the temperature or concentration, so we can vary the etch rate. So advantage for this one is we can make the reaction faster, and we can do for a larger feature size we can do it quickly. But we will be having a poor control because of the variation in the ambient temperature, ambient humidity, and all these things that affects a lot. Okay. Wettage process can be highly selective. So wettage for the through holes of in a silicon, so that we will see in a silicon, if you want a through hole that can be selectively can go can etch, okay, selectively. This sometimes anisotropically in the sense it can etch for a particular in a particular direction. Let us say to 111 direction of the silicon, it can etch easily. So that if you are taking a wafer with 100 plane, so that will 100 plane it selects faster than the other planes. Okay, so so you can make a hole through that. And another one is then liquid phase reaction. Liquid phase reaction is very easy to do. You can do which is very easy to do and very cost effective. You just need to use some chemicals and you can just do that. But disadvantage of this one is you will have more particulates in this case, while because there may be some particles will be there, definitely will be there in the agent, or some other particles can come inside, so they can contaminate. Okay, so surface energy issue will be there. So these are the things. Okay, let me check once. So HF, isotropic etch. So this is HF is used for SiO2. Okay, HF is used for SiO2. We will see this is the wet etch process. You can make a solution of HF. That we will see how to make the what percentage of HF you will get from the market, and what in concentration you need to make the solution. Okay, so this 49% of HF of concentration with the deionized water you will get from the vendors from the outside. So this is the 49% concentrated. So HF is consumed, so H plus changes, and hence the H rate changes. So as so there is some concentration, whatever the concentration, let us say 49% of this HF you are taking in what is 250 in volume ratio. One part of HF, that is 49% of HF concentration, and 50 parts of H2O DI water. Okay, so this concentration, because HF is highly kind of you can say this is very dangerous. Okay, so HF this this is used sometimes for to remove the native oxide film, which is 1 to 2 nanometer of the film, which is this concentration is used for some processes. Okay, So and we have to take care while using the HF, because this is very dangerous, and if touches the skin, so it will go inside and etch your bones. Okay, so it is very painful, that is very painful, and this is really very dangerous. You need to take care of that. So this SiO2 reacts with HF, forming this complex. Okay, this complex is soluble in water, and it will get out, so it will form 2H2O. Okay, which is also a solution soluble. So this is a forward reaction that will keep happening until SiO2 is there. So if you keep, if the if the concentration is lower and enough HF is not available, so then it won't be able to etch SiO2 completely. Okay, so that is the case. So this HF, the concentration H plus should be enough, so that uh, this H rate should be constant. Okay, so it should be a reaction rate limited, not a diffusion rate limited, because if the concentration decreases, then the H rate will change because of the concentration, lesser concentration. Okay, if the concentration is enough and it is a reaction rate limited, then reaction will be constant. Okay, then the another thing is you can use a buffered NH4F to maintain the concentration of H ions. Okay, this NH4F you can use with the it will give you HF. Okay, it will give you HF, and this is a kind of a reversible reaction that you can you will have a constant concentration of H ions. Okay, so it will give you a constant H rate. Okay, and this is also called as buffered oxide H, BOE. Okay, so you just need to mix 49% of concentration as purchased from the market of the HF with the 40% of NH4F in various proportions. You can mix, so 1:2, 1:4, 1:5, whatever, so that you can find a table also on the internet, so which concentration will give you that H rate. Okay, so also along with the H rate it is given. What are the disadvantages? Like it may contain surfactants. Okay, not the disadvantage, the surfactants in the buffered this NH4F, you can directly purchase this BOE, buffered oxide H, from the market, and they may mix some kind of the surfactants that can improve the wettability of the silicon, so which is desired for, because after the etching SiO2 from the silicon, so it is highly hydrophobic, so water doesn't stick on that, so you can improve the wettability by using some surfactants, so to improve the subsequent processes, like maybe lithography you are doing. If you are doing the lithography, that will be much better. Masking layer Si. Okay, so SiO2 sometimes is used for the masking layer, or you can use the silicon masking layer for because HF doesn't react with silicon. Okay, HF doesn't. If you want to protect certain area over the SiO2, you just deposit silicon over that, and that can selectively etch the SiO2, not the HF, not the Si. Okay, it is not the directional specific, but it is a isotropic, so it will etch uniformly along the all the directions. So this is the H rate of the HF. Okay, which was the like 49% of HF you will get from the market, and this 49% you will dissolve, you will mix it with water, 1:1 water. If you will mix, the H rate is more than 1000, that is it's around 1100 here, 1100 at this point, 1100, around 1100 angstroms per minute, that is 110 nanometer of nanometer per minute you will etch at 21 degrees Celsius. Okay, so etch rate increases with the concentration of the HF. Okay, more is the concentration, more is the reaction rate. Okay, so this is kind of a, a diffusion limited because reaction is happening faster, but you just need to have enough molecules of the HF. Okay, reaction is faster but diffusion is the problem. So if you decrease the concentration, so then it is the reaction rate, or we can say the H rate will be decreased. So for a silicon nitride etching, you can this BHF and HF can also be used for the silicon nitride etching. So but the etching of silicon nitride is much slower because of the high quality of the more is the quality, better is the quality of the layer, the lesser will be the etch rate. Okay, because of the density, this kind of the high quality films are more crystalline, more dense kind of the films are there. That's why the etch rate will be slower, the nanometer per minute. Okay, and the photoresist is not a good mask because it also dissolves in this HF. So you cannot use the photo mask. After some time it will get dissolved as well. So the selectivity is poor selectivity. Photoresist has a poor selectivity, low selectivity. Okay, due to long etch times you cannot use for the silicon nitride the masking for the silicon nitride, but you can use silicon for the masking. Okay, so another thing is, so boiling H3PO4 is used for silicon nitride or SiO2 stack needs to be etched. So etch rate of silicon nitride is 10 nanometer per minute, but etch rate of SiO2 is 1 to 2 nanometer. So there is a very good selectivity kind of. Let us say the etch rate for this SiO2 is 2 nanometer per minute. We are taking the highest 2 nanometer per minute, but the etch rate for this silicon nitride is 10 nanometer. The selectivity, if you want to selectively etch nitride, then 10 by 2, this is 5. Okay, the selectivity S is 10 by 2. So this SiO2 can be used if you want to etch a 100 nanometer thick layer. 100 nanometer thick layer. So how much thickness of SiO2 will be sufficient for this one is let us say divided by 5, which is equal to 20 nanometer. Okay, for the safer side you can deposit 30 to 40 nanometer of SiO2 and you can etch 100 nanometer of the silicon nitride film with boiling H3PO4. Okay, so the selectivity is required because so that the underneath to that mask layer, okay, that SiO2, so that silicon nitride should not get etched away. Okay, so etch rate dependence. So now the another factor how the this etch rate is depend on the method of deposition. Okay, so there are several things. So etch rate depends on the film quality. More the dense of the film, lesser will be the etch rate. Okay, deposition method. There are several deposition methods through which you can deposit the films like CVD, PVD, or PECVD. There are and thermal oxidation. Like if you want to deposit SiO2, you want to there are various methods: PECVD, e-beam evaporator, and some physical vapor depositions. In that sputtering also come. E-beam evaporator is also a physical vapor deposition, and this through the sputtering also you can deposit SiO2. And another means are chemical means, which is PECVD, and another method is native oxide growth, which is the thermal oxidation, wet oxidation, dry oxidation. In these there are several various methods of depositing SiO2. Okay, there is one example is given here. So for PECVD SiO2, the H rate is 300 nanometer per minute. For thermal SiO2 it is 90 to 100 nanometer per minute. Okay, so more, even it is at higher temperatures. Okay, this is at lower temperatures. This H rate is very high. Okay, because of the quality of the film of SiO2 is not that good with the PECVD, but it is very good quality of with the SiO2. This kind of SiO2 is used for the electronic applications, for CMOS kind of applications it is used. And also this depends on the temperature. The reaction rate of the reaction depends on the temperature, which is the kinetics, that depends on temperature. And impurity in the films, if it is doped, highly doped, less doped. So if it is highly doped, which is also used as a stopping layer, okay, as stopping for the etching. So highly doped SIs, like P++ doped, it won't etch the highly doped films. Okay, so that is the case. So these are the parameters on which H rate depends. Okay, now let's come on the silicon etching. Previously we have seen the nitrides and SiO2 oxide etching. Now how to etch the silicon? Okay, so how you can etch the silicon is hydrofluoric acid, nitric acid and acetic acid. This nitric acid will oxidize the Si. Okay, Si to SiO2. Okay, this SiO2 will be removed from the HF. This HF will form a complex with this silicon and it will form H2O and some complex. That complex is soluble in the water. Okay, in water, or we can say this acetic acid. Acetic acid is used with the replacement for H2O. Okay, for the replacement of H2O. We will see step by step. So why this H2O is not used, instead we are using the acetic acid. Okay, so simple mechanism is oxidation. HNO3 will oxidize Si to SiO2. This will dissolve, this HF will dissolve this SiO2, and the transport CH3COOH is a simple solvent to transport the reactant and products. Okay, this is used. So we will see the detailed mechanism explained by the electrochemistry. So why this CH3COOH or acetic acid is used instead of the H2, and in the next slide that will come. So we are not going that much into detail, but you can find on the internet there are very good solutions to that. Okay, so while etching, so there are some redox reactions are happening. Okay, one is oxidation and reduction are happening at the same time. So there will be simultaneously oxidation and reduction is happening, so that's why there is a redox reaction. Okay, so silicon is converted into Si++ electron, that is the oxidation of the silicon, so which happens at the anode, because as we have seen there were micro electrochemistry is going on the surface of the, there are some positive and negative kind of domains are there. Okay, so because of that there is some, at anode there is oxidation, at cathode there is reduction. This Si plus is getting converted into silicon. So these reactions are at some point, this reaction is happening, at some point this reaction is happening. Okay, so they are happening simultaneously, and that is why this is the redox reaction. So where is anode and cathode? The points on the surface randomly become oxidation and reducing sites. That is because of the etching. Okay, because of the etching, because of the etchant that happens, these points are randomly distributed over this. Okay, oh, if we are giving sufficient time, these differences average is out, because these are kind of a randomly moving domains, not a static kind of. If the domain is positive for now, that may be negative for after some time. Okay, so these are kind of random. If that does not average out, then the H is non-uniform and you will get some more too much of roughness over the surface. Let us see the isotropic silicon etch mechanism. So oxidation at anode, what happens is silicon is converted into silicon Si2 plus, and giving 2 electrons. Reduction is happening NO2. So from where this NOT is coming, that NOT is coming from HNO3. Okay, that we will see in the next slide, from how from HNO2 we are getting NO2, and from where HNO2 is coming, that we will see HNO3. Okay, there is a kind of a cyclic reaction where we are getting getting this NO2. Okay, it will give 2 electrons which will be converted into NO2 minus. That should be 2 minus actually. So formation of SiO2, this Si2 plus will react with OH minus. OH minus will be there because of the solution itself. Okay, that we will see in the next slide from where it is coming. Okay, that is no. So this is converted into SiOH, and that SiOH will be converted into SiO2. Okay, this is the reaction kinetics, which is more feasible towards this direction, and that will happen. So now this SiO2 will be etched by the HF. SiO2 will react with the 6 HF molecules, and that will be converted into, this Si will be converted into soluble complex, which is H2SiF6 and H2. These both are in the this is dissolved in the solution, and this is already a liquid form, so that will go out. Okay, that won't affect this. So now now what is the role of HNO3? Let us see the reaction. So but ultimately it provides NO2, which is required for the oxidation of silicon. Okay, this HNO3 will be this is acid, which will give H ions. Okay, this will give H ions, NO3 minus plus H ions, 2 molecules of HNO2. So this, there is HNO2, let us say a molecule of some molecules, because of the impurity. These are liquids which are not that much pure, but there will be some impurity, that can be HNO2. Okay, there can be HNO2. This HNO2 will react with HNO3, will give us NO2 and H2O. Okay, this NO2 will react with 2 electrons that were there from the Si. Okay, Si is converted into Si2 plus 2 electrons at anode. Okay, this reaction is from these 2 electrons will react. This NO2 is reacting with is converting this to the oxidation. Okay, that is the thing. So this these will be converted into NO2 minus, twice of NO2 minus. Okay, twice of NO2 minus. This 2 NO2 minus will again react with the H ions, will give HNO2 again. These one HNO2 molecule is giving us 2 HNO2 molecules. This is like a kind of the exponentially it will grow. Okay, twice it will grow, not the exponentially, but twice it will grow. So kind of exponentially only. So these kind of reactions are happening, and we are getting HNO2 from, like, this is a kind of cycle. Okay, so we just need a limited amount of HNO2, and that will be there. Thankfully, some of spontaneously generates in HNO2. This HNO2 is there already there is in HNO3, because of HNO3 doesn't come so pure. Okay, that is why. If there is okay, let me check. Okay, okay. If hmm, but we need to wait for some starting HNO2, because if the concentration of HNO2 is very less, okay, then we need for the induction period, for after some time it will be converted, we will get enough amount of HNO2 to start the reaction further. Okay, so else what we can do is we can add NH4NO2, so that will provide us HNO2 and it will start the reaction. Okay, we need to do the induction, kind of the induction period, or we need to induce the reaction deliberately. So and subsequently this is a cycle, so this HNO2 is auto catalytically regenerated, and the reaction will be more faster and faster. Okay, the rate of the reaction will get faster as we increase give the time. So another question is why acetic acid in substitute of water, why it is there. So the dielectric constant of acetic acid is less than the water. Dielectric constant of water is about 80, and this dielectric constant of CH3COH is around 5 to 6, in between 5 to 6. So what is dielectric constant? This is the shielding of the charge, okay, that generates H from HNO3, which is converted from HNO3 to H plus NO3 minus. Okay, so okay, we will come back on this point. Let us go on the further one. So we will come at this point. So oxidation is limited by the amount of dissociated HNO3. Okay, the amount of HNO2 plus HNO3, if more HNO3 is dissociated, okay, more HNO3 is dissociated, so then there will be the amount of HNO3 will be lesser, so the HNO2 plus HNO3, this is limited, this reaction will be limited by HNO3. Okay, so we need to have enough HNO3 so that we can convert this HNO2 to NO2. Okay, so that this acetic acid makes sure of that this in HNO3. If it would be water, then the dissociation would be more favorable. Okay, HNO3 to H plus plus NO3 minus. So this dissociation would be more favorable in case of the water. Okay, so that's why this acetic acid is used. Less dissociation of HNO3, more oxidation. Okay, more oxidation of HNO2 and more H, because more oxidation in the sense is Si is converted into SiO2. Okay, so more oxidation, when will be the more oxidation? More NO2 will be there, then only there will be a more oxidation of SiO2. So that will be, there will be more etching of SiO2, because this reaction is limited to the SiO2 conversion. Okay, this reaction is this S rate is limited by this SiO2 conversion. Okay, this SiO2 conversion. So okay, so now these iso-H curves. Iso-H curve is the concentration of the concentration of these solvents or these reactants. The are okay, wait, so this is the concentration profile of so if you put a straight line over here, you put a straight line over here, this over this side, so at this position, this concentration profile, there is a concentration profile that will give like 10% of this HF, and oh okay, whatever this is, this thing 90% of okay, this is kind of okay, I had put something kind of this should be here, this should be here. Okay, the 30% of this one. So these lines should be parallel. Okay, this line should be parallel with whether this cut is given. Okay, this line should be parallel in this direction to this line, this line, these lines should be parallel. Okay, so iso h curve gives you the h rate, the constant h on this curve. Okay, so on these curves, the h rate is 5.75 micrometer per minute. On this curve, this is 16.5 micrometer per minute. So this will give you a concentration. Which concentration do you require for the constant h rate? Okay, so so all these concentration on this line will give you a constant h rate. Okay, so so this is the like iso h curve. So in iso h curve also, so at this position you can see that this is kind of a parallel to this one. So whatever the concentration from 60 to 100 or 60 to this 90, so whatever the concentration you vary, this hf, whatever the concentration you vary, there is no change in the h rate. Okay, this h rate is 5.75 micrometer per minute. Okay, or whatever is the okay, this is the h rate, which is 16.5 micrometer per minute. Okay, this is the thing. So and these are the contour lines over which there is a constant h rate. Okay, so this is the thing. So in this at this position this goes parallel, so constant of you can say this hf. Okay, lines of constant and constant of this HNO3 is, the concentration of HNO3 is constant in this one, but we have varied the HF. Okay, and that is not affecting the H rate. If HF is not affecting the H rate, what is the you can say this you can say there is not enough SiO2. Okay, if you are increasing or decreasing the HF concentration, that is not affecting. Okay, so this is reaction of SiO2 formation of SiO2 limited. Okay, so you need to this H rate depends on this etching of SiO2 or silicon. Okay, we are this is for the silicon. Okay, for silicon, this silicon etching depends on the concentration of HNO3 at this position. Okay, for this region, this it depends on the on concentration of HNO3. That is because if HNO3 is not that sufficient in this case, okay, very less amount of HNO3 is there. If we just need to increase the HNO3 so that can convert the Si to SiO2, because SiO2 is not sufficient, not in the amount. Okay, SiO2 is not forming at all. Okay, so if SiO2 forms, in this case SiO2 is forming, but at this location that you can see, at this location SiO2 is forming. Okay, because we have enough HNO3, but this is parallel. Okay, this is parallel to this one, and parallel to this one, and what we have is HF concentration is, let us say, about 5%. This HF is not sufficient to etch SiO2. Okay, waiting on SiO2 etching. At this position it is waiting for SiO2 etching. At this position it is waiting for conversion of Si to SiO2. Okay, so this is the thing. Okay, now let us go on the other side. Okay, now uh, at this position that you can see, this is the cs through ch3COH diluent in this solution. Okay, we have used ch3COH, and uh, another one is the H2O. These dashed lines are for the H2O, and another one is for the acetic acid. So in this case, a longer diluent period is required. Okay, a longer diluent period, in the sense the HNO3 is not sufficient, or we can say we need HNO2. In this case, HNO2 is very small in quantity, which is not sufficient to convert the Si to SiO2. Okay, so we have silicon on the surface, gives oxide freeze. So we have not enough SiO2. That's it. Okay. And in this case, if you are in this regime, you will get a very kind of rough film, because as soon as Si is getting SiO2, then that is etched away, and which is not covered with the SiO2. Okay, if you are in we can say in this regime, then your you will finally get a very rough surface. Okay, that is not desired. And and in this regime, what you will get is SiO2 is there over the surface always, but HF is not there that in that amount. So your passivation will always be there, SiO2. Okay, so the roughness of the film, there will be always be 3 to 5 nanometer of SiO2 over the film, which can protect the Si. Okay, which can protect the Si. So that will give you a smoother film after the etching. Okay, so now let's go on the, this is anisotropic etching, silicon etching. So typically what the etch rate for 100 is much faster than 110 and 111 planes. So that is kind of, if you have a surface which is terminating with 100, orientation of the surface orientation is 100, so you will get a this kind of profile, you will get a this kind of profile over that. So and so this is terminated at 111 surface, which is 54.7 degrees. This angle you will get a 54 point, because 111 plane is not is not removing. Okay, this silicon is not removing on the 111 plane, which is not which is an anisotropic etching. Okay, so 100 plane is etching is much faster than the other planes. Okay, that is right. So there are some like we can say advantages of this one. So you can get a perfectly this kind of shape in this one, which is kind of vertical. For this is 110 orientation surface, 110 oriented surface. So for that you can get a very good aspect ratio. Okay, so this is thing and we are not going into. So these are for the hydroxide. So this is the same kind of that. So first you need to convert this Si to SiO2. Okay, silicon to silicon dioxide, and then this can be removed, formation of the soluble complex that can be removed with kind of KOH, NaOH. But this one thing you need to remember is this KOH and NaOH, these are contaminants. This alkali metals, K plus Na plus Na, so these are the contaminants for your wafer. So if you etch your silicon with this KOH or this Na plus NaOH solution. So what you will be losing is this, you cannot use this for CMOS applications, but TMAH you can use. This is tetramethyl aluminum tetramethyl amine, okay, ammonium hydroxide, or I think we will see. So for CMOS applications you cannot use, because that will contaminate your wafer and it will kill your devices, okay. So that is why you cannot use. And also dedicated hood and tweezers are used for CMOS processing, but you cannot use the metal tweezers. You always you need to use, you cannot use Borosil glass beakers, okay. So these glass beakers are only quartz beakers are used for the cleaning of these substrates, okay. And because there are contaminants, sodium ions are always there in the sodium, magnesium, potassium. These ions are always there in the beakers, in the glass, okay. They will get etched and they will go inside your wafer and will kill your devices, okay. So in this case anisotropy is also very high. For 100 surface, the H rate is 400 is to 1. For 110, this is 600 is to 1. So the H rate is very high, so you can use that, okay. This is tetramethyl ammonium hydroxide, which is used for the CMOS applications, okay, because there is no alkali contamination is there. And the H rate for Si100 is typically 1 micrometer per minute, but these highly doped P++ layers are used for to stop this H, okay. So and in this case the anisotropy is lower if you use TME. This anisotropy is lower, so mostly kind of isotropic etching is there for the all layers. And hard masks are used. This silicon nitride or silicon dioxide or aluminum is used. So the selectivity is very good for silicon nitride and silicon dioxide. Silicon nitride is much better masking layer for silicon, because it doesn't dissolve in tetramethyl ammonium hydroxide. So that will protect the layer underneath, okay. So why anisotropic? Because this plane, the one plane oxidizes faster, so which affects the etching, stronger effect of at etching of at from 0 to 100 degrees. And the complex, then what happens is as it oxidizes faster, there will be SiO2 is the complex agent to dissolve SiO2 is absent. No HF is there, okay. So this SiO2 can be used for okay. Okay, so in this case what happens is this Si is converted into SiO2. That particularly 111 plane oxidizes faster, which protects the underneath layer of the silicon to dissolve, okay. So because in this case this okay, this if you see that SiO2, this selectivity is very good in this case. So if once Si is converted into a SiO2, but in the previous case we are deliberately converting the Si to SiO2 so that we can dissolve in HF, okay. But in hydroxides we are not using the HF at all, but this hydroxide itself makes a complex with silicon that is dissolved, okay. So this what happens in this region is 111 plane oxidizes faster, so that protects the underneath layer, because SiO2 is not dissolved in any kind of hydroxides. Okay, so that is why. So this stronger at etching temperatures. So because at up to 100 degrees it is not that much, it is protecting the mm, layer underneath. Okay, it is not dissolving in the SiO2 in the hydroxides. And complexing agent to dissolve SiO2 is not there. Okay, because there is no HF in this solution, so that is why SiO2 on Si is protected, protects silicon underneath. Okay, that is the thing. So SiO2 on this rate, hmm, that is the thing. So what you can do is you can make through holes or like this. So every time, so because of the anisotropicity and anisotropic etching, so whatever design you will make over the sub wafer, so you will get a square kind of trench. Okay, you can make a through hole through that, because of the etch rate of the Si 100 is much faster. This is kind of a trapezoidal kind of profile you will get. So it, if the hole is not enough, so it will, you will get a conical, not a conical, you, that is ending. Okay, when you won't get a through hole, but that will end soon at this position, so you won't get any kind of through hole if this the size of this is smaller, the opening is smaller. Okay, so the hydrofluoric acid is very dangerous, so you need to take care of that. So, and actually it just looks like a water, so it is very color, it is colorless, it is odorless, so you won't get any smell of that out of it, like ammonium hydroxide or anything. So so you need to just take care, colorless. And so it is very dangerous. If it falls on you, so it will go inside your skin and will etch your bones, and that is very painful. So you need to take care of that. Whenever you are doing, you should wear you should take every measures. Okay, need only 1% of body exposure to because a systematic intoxication and exposure. So initially you won't feel any pain, but after some time, when it will start itching your bones, so it will be uncontrollable and unbearable pain. So so what do you, if you know that HF is spill on you, so just immediately uh, immediately rinse your hands and apply the calcium gluconate gel. Okay, so this gel will neutralize that hydrogen HF over there with calcium. So because calcium in our bones will be degraded, decalcination will happen inside our bones, and if you already applying the calcium, or that will neutralize that effect and will before going inside your body. Okay, so that you need to take care. So while whenever you are doing, you are dealing with the chemicals, any kind of chemicals, every chemical is hazardous. Okay, so ammonium hydroxide or trimethyl ammonium hydroxide, all are like toxic to your health. So you need to wear face shield, so that it should not spill in your eyes while pouring or something. You need to wear chemical goggles, not the glasses, so that you can protect your eyes. So you need to wear the apron, so anything should not fall on you. Long sleeves, so because your lab coat or whatever you are wearing, that is not proper, that can penetrate, but these are F-talon gloves, so these can protect you. Okay, and closed-toed shoes which can protect or direct spilling on you. Okay, so these are things that you need to take care. So thick nitrile gloves are there to handle these, which are F-talon gloves, you can say, and these are the thin nitrile gloves for the general purpose. If you are using the solvents, then you can use these thin nitrile gloves, which are sufficient to block the solvents. Okay, but thick nitrile gloves are required if you are dealing with the acids or bases, which are very toxic and are very dangerous. These latex gloves are won't will not save you from any kind of chemicals, whether these are solvents or any acids or bases. These won't allow you. These vinyl gloves are not used at all for any kind of chemical means. Okay, so that's it for today. So let's end the session here. If you have any doubts, you can ask me now, or you can ask in the next session as well if you have any doubts. Okay, so let us see. If you do not have any doubts, let us close this session for today. So thank you for joining the meeting. So you can ask the question on the forum, or you can write to me. Thank you.